And he will present the results of the assembly part of the first CAMI challenge.
Yeah, thanks. Okay, so I think it's time for first results. This is about assembly. Again, what's this? Okay, so here are the data sets again. So we are looking at 3 different data sets: low complexity, medium complexity, high complexity. Just as a reminder, I will come to this later. Actually, I have like many slides and many like figures and different slides for the different data sets. I will focus actually on the high complexity data set, and we can go back to the low and medium and low complexity data sets maybe later if you're interested. But I think you see the most important effects on the high complexity data set best, because you can sort of average, get some sort of average across the different genomes we are looking at. So first of all, what do we want to get out of the assembly? That's the first question we want to ask, and I think this is very important for the evaluation of an assembly. I think biologically it's not very well defined what you want to achieve with an assembly, right? Because some people are interested in reconstructing whole genomes from organisms, right? So you want to run an assembly, you want to run a binning, and at the end you want to look at the complete genome, basically. But maybe you're only interested in reconstructing genes, but you want to do this as precisely as possible, right? So don't do any mistakes when you reconstruct the genes, but you don't care about like long context, let's say, right? Because you want to maybe look at the community structure for a particular gene or a bunch of genes, and maybe look at genomic variation for these genes. So that's a very different question, right? So here you're interested in making as few mistakes as possible. Up here you might be more interested in contiguity of your assembly to reconstruct, let's say, operons or things like that. And it's fine if you make single mistakes in these kinds of assemblies. So depending on the question you are asking, the question is what kind of tool do you want to use? And I just want to show you some, like, as a brief reminder why assembly is a problem, just some slides where you see in this case, the effect of the CAMI size. So you run an assembler and you choose usually you have to choose a CAMI size for your assembly. And this is an example I took from the Bandage webpage, basically. Bandage is a tool that visualizes a De Bruijn graph. And this is looking at a Salmonella genome with 100 base pair Illumina reads. And this is an assembly for 51 mer, basically. Right? And what you see is that everything is like entangled and you don't really see the genome structure. If you increase the CAMI size, it looks much nicer now. You get longer stretches of context, and you can go on with longer CAMIs, and it seems that you are now getting at your genome, basically. And so you can keep going. Next CAMI size is 81. So the problem is, while here you still have connections between the different contexts, here everything breaks apart, basically. And if you go over a certain limit, then you end up with your reads, basically, right? So this is the first question: what CAMI size is the right CAMI size? And even when you do an isolated genome assembly, you don't really know which one is the right one, right? So you start optimizing the CAMI size even for single genomes. So how do you want to optimize this for a metagenome? And then, of course, what makes these loops here are the repeats in the genomes, right? So if you look at repeats, it's actually, then this is what we discussed before. When you want to resolve repeats, then the read length matters, right? So for long reads, which are longer than the repeat, the assembly is actually very easy. If the repeats get shorter, if the reads get shorter, you might be able to resolve some repeats using like paired end information or so on. But if you have really short reads, then it's really a hard challenge to assemble these genomes, right? And when you look at a metagenome, in a metagenome, you not only have like very different isolated kind of genomes, but you have strains in your metagenomes, closely related genomes, and then basically these different genomes look like large repeats to the assembler, right? And it's a particular challenge for the assembler. Okay. So what we are going to do now is we are looking at these different assemblies, and we are going to evaluate the assemblies. And what we are using for evaluation are different metrics. These are the metrics we are using. You can look at basic statistics like the number of contigs you have for an assembler, the number of large contigs, for instance, contigs which are larger than 1 kb. You can look at the largest contig, the total assembly length, and so on. And you can compute the N50. I think I don't have to. Do I have to explain what N50 means? Probably not. Okay. And actually, we are focusing on reference-based statistics, where we basically map everything back to our references, as we have all the references available. So the kind of alignment-based statistics you can do is like the genome fraction, % of genome you are recovering. So down here is our reference genome. These are the contigs from an assembly. You map the contigs based back to the references, and then you just see like what percentage of the reference has been reconstructed. That's the genome fraction. You can look at duplication ratios. So these two contigs here are actually overlapping, and then this part of the genome is duplicated. You can look at the number of gaps or the length of the gaps. Basically, you can look at the largest alignment length, or you can look at the number of unaligned contigs, which is weird because the assembler generated something which is not even doesn't exist in the reference. We are using MetaQuast for this kind of evaluation because it generates all these measures. And when you run MetaQuast on a metagenome assembler, you basically get these statistics, right? So this is all of these numbers are generated and put into a file, basically, and then you can start looking at each of the, in this case, each of the references and see which assembler does the best. So to do these kinds of evaluation, we have to look at our gold standard, right? Because we are comparing back to the gold standard. So let's look at the gold standard. How do we generate the gold standard? What we do is, well, actually up here we have the reads, like the raw reads from all the genomes we got from our data contributors. And these reads we assemble to these initial genomes, basically. And you end up, of course, you end up with a number of contigs because you usually don't get a closed genome from such an assembly. So this is our initial assembly. For all of these almost 700 genomes, we ran assemblies using the same assembler. And then we discard all the contigs which are shorter than 1 kb. And then from the contigs which are longer than 1 kb, we simulate the reads with a pipeline Andy presented earlier. And then we look at the coverage, right? And the coverage depends on the abundance distribution which you specify while running the simulation pipeline. And whenever you have coverage which is larger than 1x, this part of the genome goes into the gold standard, right? So the gold standard is something which none of the assemblers will ever achieve because usually they need higher coverage than just 1x coverage, right? But anyway, this is what we call the gold standard. And this is also what's being binned and profiled in the other two challenges, basically. Okay? So we use the gold standard for all of these 700 genomes to map the assemblies back to the gold standard or to the reference. Okay. So let's look at the high data set. This is weird here. This is a high complexity data set. 540 genomes. We have 54 evolved strains, almost 500 plasmids. We have 5 different samples. That was a time series where we changed the abundance just a little bit, not that dramatically. And then overall we have 75 gigabases and 2 by 150 base per reads. So what I did first is I looked at, oh, this is hard to see, but anyway, this is as Andy said, we did a pairwise comparison between all the different genomes, basically, to come up with an average nucleotide identity score between all the pairs of genomes, right? And this is a heat map of the scores, basically. What you see are the genomes here. This is a matrix of all the genomes in the high complexity data set. And the color is the ANI, the average nucleotide identity. What you see are these boxes here. These are basically the evolved genomes, right? So there is one genome, like one real genome, and then we evolved, like in this case, maybe 10 genomes out of this real genome, and they cluster nicely, right? But what you also see, and as I said, it's like how many, like 54 strains in here. But what you see is these are probably more than 54 closely related strains in the data set. So there are genomes which have some sort of similarity to other genomes in the data set. There might be already different strains, right? So we had genomes from different strains, which we didn't have to simulate. And you see these clusters showing up with the real genomes, actually. But what you also see is that there are some genomes which have some average nucleotide identity across many of the other genomes, and we actually have to make sure that this is not a problem for the evaluation. It might be actually a problem of the script that calculates the ANI. So maybe these are high identity regions, but only very short parts, small parts of a genome. So we have to go back and check these. But anyway, you see some genomes which have pretty high coverage, pretty high similarity to different genomes. Okay, so then this will be important for comparing the related strains, right? See how the related strains perform and how genomes perform which don't have any close relatives in the data. Okay, and then the first thing you can look at is the genome fraction, like how much of the genome is actually recovered from the different assemblers. So what you see here, these are the different assemblers. Whenever there is the same color, it means this is actually the same assembler running with different parameters or maybe different versions of the assembler, right? So the yellow ones might be, I don't know exactly, actually I don't know which kind of assembler it is, but it could be an assembler where you ran different KMO sizes, let's say, right? And then you see the effect of the different KMO size on the assembly. Okay, so same color means same tool. Each dot is a genome. It's one of the genomes in the data set. And then for each of the genome, you can specify the genome fraction. Okay, as you see down here, this is the gold standard. Like for the gold standard, almost all genomes are covered completely. And that's because they have high enough coverage that there is a read like across the whole genome. 1x coverage. But some of the genomes which have very low coverage are only covered like 50%, and none of the assemblers should do better than what the gold standard is here for this particular genome. Okay, that's clear? Okay, and then the box is this is basically a box plot for all the different genomes in the data set. And you see the median, the line here is the median genome fraction. And what you see clearly is that, well, when you look at, well, which one's the best one? What would you say? Which one is the best assembler? Yeah. Well, you can clearly say that this is doing pretty bad, right? I mean, this assembles nothing, basically. I mean, for basically all of the genomes, like the maximum genome fraction is like, I don't know, 30%. So this is obviously the worst assembler in the data set. But then deciding which one is the best is actually pretty hard, right? Because the orange seems to be pretty good. This one seems to be pretty good. The median is pretty high. And this pink one seems to be pretty good.
Oh, we want to look at many measures. Maybe some are good in one thing and not.
Exactly. So you can look at the next measure. We will do so. So first of all, let's separate the data set again, because we have these closely related genomes, with an ANI of more than 95% identity, and genomes which have less than 95% identity. And when you separate the data set, you already see some effects here.
Sorry, one more question. Why do the two assemblers have been broken next to it?
The broken just means that they assembled scaffolds, right? But we are looking at contigs here. So that means the scaffolds were broken into contigs for the evaluation. Otherwise, it's hard to compare, right? If you have an assembler that generates contigs and you have an assembler that generates scaffolds, you don't want to compare this. So broken doesn't mean that the assembler is broken, but just the assembly itself was broken into.
And the terrible one there looks like it's the same orange as the good one below. Is that really the same?
No, it's not the same. It's a different one.
Okay.
No. Yeah, you're right. No, it's
Different
a different.
parameters.
It's a different one. Yeah.
Shade of orange.
Yeah.
Okay.
Okay. So now let's separate the genomes into closely related, the ones which have closely related genomes in the data set and the ones which are unique in the data set. And then the whole plot looks like this, right? So these are the unique genomes where each of the genome doesn't have any other genome in the data set which is more than 95% identical, right? And you can see a clear effect here on these strains. Basically, it means whenever you have a closely related genome in there, the assembly breaks, right? For unique genomes, everything is fine, and it looks really nice compared to the gold standard here. But anyway, so the median is almost like 100%. But for genomes where you have closely related strains, or our simulated strains, the assembly basically breaks into pieces.
Is that separated after the binning or before, after the assembly or before the assembly?
Well, after the assembly, of course. Yeah. No. This is after the assembly, right? So we just look at, in this case, we look at genomes which have close relatives and then just plot the matrix. Yeah.
Do you have an explanation why even the gold standard seems to have like much less genome fraction for the close related strains?
Here?
Because I mean, in the gold standard, we should, in theory, be able to exactly tell those apart. And it looks like now with a high N we have.
Well, the gold standard, this if you combine these dots and these dots, you get exactly this one here.
Yeah, exactly. But I mean, maybe it's just what I'm seeing. But for the ANI below 95%, like we have always 100% genome fraction.
Yeah, this is just by chance because like this is like the high coverage genomes are all unique genomes basically.
Right. Okay.
Right, and the low coverage genomes are just by chance genomes which have some closely related genome in the data set. Okay, and then you can look at and you can plot this differently again. Right, this is the next try to visualize the data. So let's see what we're looking at. So now we are looking at the genome fraction again. Okay, and down here is the coverage of the genome. It's in log scale, and each data point here is one genome again, and then it's colored by the different assembler. So you have lots of data points here, right? For each of the genome, there is a data point, and times the number of assemblers, basically, right? And what we are trying to do with these lines here is some sort of like, well, let's say moving average, right, across the genome. So if you have some sort of like you take the average of like these values here for this pink assembler, and then we try to smooth this into a line to get some sort of trend, right, for a different assembler. So let me remove the dots here, and it's maybe little bit easier. But now you know how we actually come up with these curves, right? And what you see is the different colors again are the different assemblers, right? And yellow means, okay, different parameters for this particular assembler. Up here is the gold standard. So for the gold standard, the coverage of the genome is not important at all, right? So you almost always get the complete genome. And then, of course, what you would expect is for an assembler, for a real assembler, not just the gold standard, if you increase the coverage, you start actually assembling something of your genome, and then the genome fraction rises, and then at some point you should get like 100% of your genome, right? Low coverage, no assembly. High coverage, you should recover the complete genome. What you also see is that some of the assemblers are doing really bad on very high coverage. So this goes up to like 1000x coverage here, and some of the assemblers cannot deal with high coverage. So all the high coverage genomes are just lost in the assembly for some of the assemblers. Others are actually doing better.
Affected by that?
Isn't that the average?
Yeah, that's the average. So this is hard to say. I mean, if all of them are actually affected by this, because this is some sort of spline that's across. So it might be we might use a different function to actually do the average.
Can you go back to the previous slide so you can actually see the little dots?
Yeah, see here, for instance, this pink one is really bad. This is like 0 here, right? But the green one, well, the green one is also pretty bad. This is here, so this is why the green goes down. But this one is doing pretty good, like this green one here. Maybe that's the same, right?
One thing I see is there seem to be very few genomes with high coverage, which is to expect it from a log normal distribution.
Exactly, most of the genomes are actually here, right?
So
Yeah.
is it possible that the sample size is maybe too small to make a conclusion based on the high coverage?
No, I don't think so. Well, you see this in I mean, I think that, you can make the conclusion that for some assemblers, high coverage is a problem. Yeah.
It's what you expected, but I'm not sure if these are really enough genomes to demonstrate this.
Well, no, I think you also see this in the other data sets, I think. So, yeah, you can make this conclusion.
In a qualitative way, you can kind of say.
Yeah. Yeah, okay, yeah, maybe.
Other people think so.
Okay.
This plot, is that the same moving average?
Okay, yeah, so now I'm trying to show you different plots and see which one what you think is the best one to understand what's going on. It's complicated. So now this is separated by assembler, right? So each of these panels is a different assembler now. Okay, but it's basically the same plot, but separated by the assembler. This is a gold standard. So for the gold standard, genome fraction is always 100%. This, I think, is an effect of the mapping, right? Because what you see, the blue are the unique genomes, the red are the genomes which have some close relative in the data set, okay? So if you have a close relative in the data set, I think this is an effect of the mapping, right? So mapping it back to the reference, maybe this missing 25% was mapped back to the close relative, let's say. Okay, and this is why you're missing like 25%, although you would expect to have like 100% coverage here.
So a mapping problem in class.
In Quast, yeah. Right, because it maps it to somewhere else.
Isn't the original data available where we know which each read comes from?
Yeah, of course. Yeah, if we use the original data, then that would be a flat line, right?
Oh, all right.
But the idea is of using the gold standard in the same evaluation pipeline is to see how the gold standard actually performs. Right?
I meant the mapping of the genome to the reads, because I mean, doesn't the read simulator creates a file, right? Which
It does.
says which read belongs to which
Yeah.
genome.
And for each of the contigs, we know where it belongs to, right?
Yeah.
If I would use this information to generate this plot, then there would be a flat line here.
You
Okay,
can't
that's what
get
I'm
that
saying.
information for one of the assemblers because that information doesn't go through and result in the FOSTA file.
Oh yeah, that's
Yeah.
And I think not all the assemblers keep track of reads.
No, the assembler don't. For the assembler, I can't do this. Yeah. So I have to map it back. Yeah.
I wonder if multiple mapping could resolve this problem. Like, I know that the mappers usually by default map only one fragment to, say, one genome, but if you define it to map to multiple places and check the, say, identity and something, could
Yeah.
it be resolved?
Probably. I don't know. I don't know the details of MetaQuad. So whenever you have Well, it's using NACMA to map it, right? So I don't know what happens if you have two alignments to different genomes which are basically identical in terms of the score, right? It should actually include it maybe in both. Well, maybe not. It shouldn't include it in both because otherwise one has like too high coverage. I don't know. I mean, we can discuss later. But anyway, so what I'm trying to say is that we have some sort of mapping effect in the evaluation pipeline. Right? But overall, it looks quite good. So when you look at the assemblers now, you see that basically I would scroll through this plot again, but what you will see is that all of the assemblers have problems with the strains again, right? And this assembler has problems with high coverage genomes, right? High coverage, low genome fraction. But here in the like the medium kind of coverage, it's doing very, very well, I think, compared to this one here, right? I mean, this is also doing well, increasing genome fraction, but it seems that this needs like a certain amount of coverage to start assembling anything, right? And when you scroll down, what you see sometimes, hey, this is looking really nice, right? This is almost looking like the gold standard except for the closely related genomes. So this is doing a very nice job. Same for this one. And then you see some effect here when you compare these. That's right. Yeah, I think so. If you look at this, I think it looks like it's shifting to the right. Right? So like this curve here is a little bit shifted to the right, and it's a little bit shifted to the right. That could be an effect of the camer size. So a small camer size would assemble all the low coverage genomes. A larger camer size assembles the medium coverage, and the high camer size assembles the high coverage. And you can see when you use a small camer, you have problems with the high coverage genomes. If you use a large camers, high coverage is fine. Right?
You can start to tell the close ANI ones apart because the area underneath the red curve is increasing as well.
I'm sorry?
So the red is for the close.
The closely related ones, exactly.
Exactly, and if those three are like three different camer sizes,
Yeah.
the area underneath the red curve
Yeah.
is increasing as you go down. So you're
If you go up with the camer size.
correct.
Yeah.
Yes, as you go down your plots.
Oh, I see. Okay, yeah, exactly. Yeah, exactly. So you see some effect on different parameters here, right? And my assumption is that these ones here use actually different camer sizes, like megahit, for instance. It starts with a small camer and then iterates over a bunch of camers, and that's why it actually picks up like all of the genomes, basically.
Again, this looks like the last dot is like one genome. And if this is a genome that is just simply difficult to assemble,
In this case, yeah. Yeah, what do you mean?
maybe the curve would be less extreme if there were a different genome, or if there were more genomes with the same coverage.
Yeah, that's right. I mean, this is doing a pretty good job here, this assembler. But if you look at, there are other assemblers like here. See, this one here. There are a bunch of genomes with very high coverage, and it doesn't assemble them. So I think you can see some sort of general trend, I think. Because when you look at the other data sets, it looks basically the same. Like the same tools have problems with very high coverage.
All right.
Okay? Okay, so anyway, you can start looking at these jobs and thinking, at these plots and think about it for hours, I think. I will just show you some other metrics. This is the total length of the assembly, right? Not the total length of the assembly, but the total length for each of the genomes, basically, which is also related to the genome fraction. You see the same trend, basically. The orange one is doing pretty good, coming pretty close to the gold standard. This is pretty bad, and so on. If you separate this, again, there's a trend that it's doing worse with the highly related genomes. You can, I will show it. You can look at the number of contacts, right? So for the gold standard, number of contacts basically means contiguity of your assembly, right? Small number of contacts, long contacts, if you combine it with the total assembly size, of course, right? Because if you don't assemble anything, and it just have one contake on this plot, it looks perfect. But if you go back to the assembly, the size of the assembly, then it makes, of course, a difference. Right? Like this one here looks really good. Right? If you just look at this plot, it's like, oh, perfect. Just we get like the close genomes out of it. But when you go back to the total length, it's also almost 0. So you have to basically, when you look at the plots, you have to combine these in your head, or to maybe do some combinations of different metrics here. And then, of course, you want to know that this is like the number of predicted genes. And again, I mean, this looks pretty good for orange and the blue one and the pink one. But it's just looking at the number of genes. So if you have a very fragmented kind of assembly, the number of genes goes up because each gene might be fragmented into like multiple parts, right? Or here actually the number of predicted genes goes down because the assembly is just worse.
The number of genes for the left side, it seems also yellow with one parameter setting is doing okay, and the blue one on the left.
Yeah, the blue one on the left. Yeah, that's true. Yeah.
One parameter of the yellow one.
Yeah, this one here looks pretty good. That's true.
So there, like most tools seem to be doing except 3.
Yeah. So what we actually should look at is not just the number of predicted genes. So what the pipeline does, it takes the context, predicts all the genes, and then counts the genes. What we could actually do is take all the genes and compare the genes to the original reference genes, and then look at like how much of the genes are actually covered. Like how many genes are covered with at least 90% of their length, right? Instead of just looking at the number of genes. So that's something we could actually do. Another analysis, yeah.
Why is there, I mean, for assemblers, I'm a bit surprised that you have this strong influence of this is whether there are multiple strains in a data set or not, right? Data divided by that.
Yeah.
And why is the performance better if there are multiple strains in a data set for the assembler?
Where is it better?
Worse.
It's worse.
Oh,
This is
right, sorry.
right.
Yeah.
This is the one where we have multiple strains. So it's worse actually.
Okay, that makes a lot of sense. Okay. And that's through the bench for most assemblers, right?
Yeah.
So as you would expect.
Yeah. Okay. And then you can look at what's this? The mismatches per 100 kilobases. So here now you see this is really bad. It only assembles like a small fraction of the metagenome and has like most of the errors. And again, orange is doing pretty good, pink is doing good, and this one also. And this is the number of misassemblies. So misassemblies would be like rearrangements and things like that, not just single nucleotide mismatches. And well, here the yellow one is actually better than the orange one, or the pink one is better than the orange one. So when you think of the other metrics, it was like orange was performing similar to pink one. So now if you look at misassemblies, I think pink one is actually doing a better job. It's doing less misassemblies, but the other metrics were comparable to the orange one. Okay. Yeah, so that's it basically. I mean, we have like hundreds of plots you can look at, depending on how you want to look at it. And as I said, it might make sense to actually combine different metrics, right? Combine, I don't know, contiguity with misassemblies or something like this, and then do another bunch of plots. So the overall trend for the other data sets is basically very similar. So this is the medium complexity now. This is the ANI score. These are the simulated strains here, which you can, I don't know, maybe hardly read here. This EVO is the evolved strain, so they all cluster together here. So we have a bunch of like dark red clusters, which are very similar to each other. And again, it looks pretty similar to the high complexity. Orange is doing a very good job here. So now I think this yellow one is actually not the yellow one from the other one, so the colors are switched, unfortunately. But anyway, so I will not go through all the details here. I just want to show you that there's the general trend is actually the same. So also for this data set, they are doing worse with closely related strains, although they are much less closely related strains here. And then let me go to the low complexity, maybe last one. This is the low complexity. Now you can actually read it. In this cluster here, these are all these evolved strains from this genome. These are the evolved strains from this genome, and so on. So you see these clusters, and here we have like I don't know, 5 of them. Here we have only 2 of them. And again, well, the problem with a low complexity is that you cannot really make these general assumptions because you only have, well, you have much fewer data points. So the box plots are really broad here. But anyway, yeah. Okay. Well, if you're interested in the plots, just go to the web page, like the GitHub, and you can look at all the plots. So let's try to make some conclusions, which is a little bit difficult, but I think we can make the conclusion that none of the assemblers perform very well on closely related genomes. I think this is, but that's something we expected already, but now we can actually see it from the data. Some of the assemblers have problems with very high coverage. So sometimes it makes sense to actually downsample your metagenome before you do the assembly. You can do some CAMI-based downsampling, basically. That might give you much better results for these assemblers. And it seems that using a range of KMers, like MegaHit is doing, outperforms just a single KMer. And also a combination of tools seem to be performing best, right? So we have some pipelines actually in there. It's not just running a single assembler, but it's like a combination of an assembler, a read correction, a misassembly detection tool, something like this. And it seems that the combination of all of these are actually performing very, very well.
So how do you, just a question, the range of KMers, so how did you come up with that conclusion? With the range of KMers?
That was this example, this one here. This one here. Remember this? This is what I've seen earlier with running like Ray on our toy data set. So when I ran Ray on our toy data set with different KMers, you see that depending on the KMer, you pick up different genomes, right? And you have problems with other genomes.
Okay, but for this data, we still have to show it in some plot because I don't know if I could. I mean,
well, if you show the tool name here and the parameters, you would see it.
Then you would see it. Okay.
Yeah.
Performs best in terms of which measures? How was that quantified?
Well, I think probably in all of them.
In all of them.
So do you mean, if you scroll down a little bit,
Yeah.
the one with the blue, those top, those guys.
This?
So you're saying that those ones use multiple KMer sizes?
That's what I think, yeah. Well, we have to look at well, I don't know. I also only look at the anonymous names here, but from my own experience, running like Ray on a data set compared to running MegaHit on a data set, I think MegaHit performs better in this kind that it actually picks up low complexity and high complexity genomes, and Ray sort of focuses on a particular coverage, let's say.
Okay,
That's basically what you do.
We have to make sure that we
different
actually see that also in these results. Right?
Yeah.
So we have to look at that then probably without tool name, without the anonymized version.
Yeah, of course. Well, we cannot really do this with, of course we have to look at the tools.
And the other one was a pipeline, was that a similar? So, yeah.
Yeah, there are also pipelines in here, right? It's not just running a single assembler, but we have, like, many of them are pipelines, actually. Like a combination of different tools.
And I think you repeatedly said that the performance, you had similar observations across all data sets. Right?
Yeah, the trend is, I think, is the same. So when you look at, for instance, the problems with high coverage here, right? This is always the case. When you look at the low complexity data set, genomes with high coverage, the assembler has a problem. You look at the medium complexity, it's the same. You look at the high complexity, it's always the same. For this particular assembler, it always has problems with very high coverage genomes. Yeah.
Do you know why, or do you have an idea why that could be?
Yeah, it's because the sequencing errors, they accumulate, right? And then it's hard for the assembler to tell sequencing errors from real KMers, right? So if you have low coverage, like medium coverage, let's say, we can still distinguish between a k-mer, like a valid k-mer, and a k-mer which is like a sequencing error. If you have very, very high coverage, you cannot distinguish this anymore. It basically looks like 2, 3 valid k-mers. Because you're accumulating the errors also. I think that's the reason.
Yeah, maybe a comment to that. Oh, sorry.
Yeah.
Because we did some experiments with error-free reads for some assemblers which had problems for large k-mer sizes, and the effect disappeared. So for perfect reads, the higher coverage wasn't a problem anymore. So
It's kind of surprising because you would expect more data to do better, and that's the effect of.
yeah, exactly. I mean, we looked at the bandage graphs for those high coverages, and you see that it's not just like a single path anymore, but it gets really tangled. So it looks like a power line, something like that. So, yeah.
Seems like it's not being tested on these cases, I guess.
Probably, yeah. I mean, for coverages, thousands, I don't know how regular that is.
Yeah.
Good point. Then.
Can I ask if somebody has a tool here in this presentation?
Do you know the name of your tool? Did you see it? Did you recognize your tool?
No,
I know, okay.
Okay.
I actually don't know which one.
Well, you should be able to tell you. Well, you should know the anonymous name for your tool. If you go online, you should see it.
But you don't have to tell us.
Yeah, don't tell us. But just in case you're interested, when you go online, you should be able to retrieve the name for your tool, but just for your tool.
Yeah, I want, and we would like to know if you agree with those conclusions. If you look at that and you feel that it's the right way to look at the data, that these are the conclusions that should be drawn from it. I mean, we will work on this more in detail in the following days, but I thought if you already have some points you would like to comment on, but
Yeah. Well, exactly. Well, let me mention something else. Maybe go back here. Where's my mouse? Let me just go back to this example. Like this one here. If this is your tool and you think this is wrong, let us know. Right? No, but so the problem was we had one data set that looked like this, right? And we thought, well, it cannot be that bad, right? I mean, nothing aligned to the references, basically. So we thought, okay, there must be a mistake. So we contacted the submitter, and then basically he submitted the wrong data set. So he mixed up our data sets, right? So now I think there's still time to fix this, right? I mean, all the others look okay, I think, but just, well, go back and check it. And actually, we try to contact these people, right? And some of them did answer, some of them didn't.
oh, that's reassuring. That means that if that one is an erroneous submission, and maybe something's wrong with the backstabbing person, then that means that most tools showed are performing okay.
Pretty okay, yeah. Yeah.
That's good to know.
Actually, so you are first now. Sorry.
Yeah, thank you. So you have mentioned that the tools using multiple k-mers are always better than the tools using single k-mers, right? And I wonder if you have, well, I guess you're using the default k-mer combination to that. Say, for example, IDBA uses 20, 40, 8, 60, 80, and 100, and Menahir uses 11, 21, 31, something like that.
Mm-hmm.
And I wonder if these combinations, well, let's say, for example, defining IDBA to run exactly the same k-mer combination will yield better or worse or the same result. Yeah, so it's just not really related to that. I just wonder if this will happen. So the same k-mer combination for multiple k-mer tools for a more
Different data sets.
Yeah.
Yeah? That's what you're saying, basically.
Yeah.
That's a good question, but that I don't know, right? I mean, the conclusion I just made is just from my own experience, right? And when as I said, we were running, so we had this toy data set before we started the challenge, right? We had this toy data set where everybody could like test tools and then look at evaluation results and so on. So I ran a bunch of assemblers also myself, right? And so in the case where I used Ray with different cables, I exactly got these curves. When I used a combination, the curve looked very different. So that's my my guess that this is actually the case, right? So when we run the tool ourselves, right, if it didn't get a submission for a particular assembler, we always use the default parameters, right? If people, like developers, submit their own results, they can, of course, tune the parameters somehow. Right? That's something we couldn't prevent them from doing. Okay, yeah?
I guess I can make some general comments from the tool developer perspective.
Yes?
So, in my opinion, what you use is state-of-the-art evaluation methods, like MetaQuest. I cannot think of something more appropriate for evaluating metagenomics assemblers nowadays. There remains the question of how do you define an order on those metrics. I mean, you have plenty of metrics which are not comparable.
Exactly.
And in other challenges for assembly, some of them have tried to come up with a single metric, which is a combination of all of those. And talking about the assembler fund. And so at least something could be designed for metagenomics in mind. So at least know actually what are your weights on those metrics. Are there some that you think are important?
Mm-hmm.
Or basically in the order that you presented them, it appears that genome fraction and number of genes is important for this benchmark.
Yeah, I think that's right. I mean, that's exactly where we want to get at, right? And this is what I put here as on my to-do list, basically. You want to come up with some sort of ranking based on your specific goal, right? And then, so let's say you want to minimize errors. So which are the metrics you have to look at, right? So you can choose an assembler which has like the less misassemblies maybe, if you want to minimize error. If you want to maximize contiguity, you look at the different metrics. If you want to combine this, then the question is which are the right metrics to combine. This is actually, that would be very nice if we come up with such a combination and maybe a single score for different questions you have in mind. Yeah, it's a very good point.
Yeah, I agree. And we had upfront also generated Ruben, Garrido, Otter did this one, unfortunately, with 60 kind of made a heat map where you basically took for every tool all the measures, and then you group them, organize them, and then the measures by default all contributed. So they were first scaled to a certain range, from minimum to maximum, what you search in the data set, and then based on that make a so they were all scaled from 0 to 1, each of those measures based on the min-max range, and then you do this heat map grouping of the different tools across the measures. And that means implicitly that the weight for every measure, the importance is the same, but you could think about manually like placing a weight and scaling them. Yeah, then of course, then other people can argue this way you manually you can manipulate also in some ways, right? Depending on how you weigh. But yeah, if you say that it's an accepted approach in the field, somehow it doesn't make, I mean, giving everything the same weight is the same arbitrary in some ways, right? So if maybe you have some good suggestions on what to group and what to weigh for which question.
It will be a matter of compromise, I think. It's going to be a matter of compromise because, as far as I can tell, there is no accepted ways to compare assemblies totally in the field.
Yeah. Well, especially, yeah, that's right. I mean, especially in metagenomics, I think, right? You might have very different goals.
I just had a couple of comments related to the errors and another thing just leading up to the discussion. Feature response curves, what might be nice to add, so that you can actually look at each reference and kind of plot how is it doing in terms of size and error, not just kind of independently count size, etc. And that kind of encapsulates all of that.
Yeah, I missed this point. This is actually something what we have on our to-do list also.
And the second thing, I don't know if you can go back to the misassembly slide.
For the high complexity?
Yeah, one thing I was looking at there, I guess that's MetaQuest output.
Yes.
I don't think it was that.
This
It was when it was
matches
divided there. But not, there was,
this one.
yeah. So for this one, on the right, we have more genomes that are more closely related. And in my experience, when I've generated plots like this in the past, when you have more that are closely related, you actually have an increase in the misassemblies, which doesn't look to be the case in this plot. There's more, depending on, again, the method, you'll walk into a very closely related genome. And I'm not sure if it's measuring that or not, kind of like chimeric contigs or scaffolds, etc. This one was a bit counterintuitive.
That's right. I agree, it should go up, right? The number of misassemblies should actually go up. It could be an effect of having, by losing assembly, basically, losing context. If they are too closely related, you might lose them completely, right? And then whatever is less, whatever is left, maybe has less misassemblies.
Right, and again, if I go back to the curves, that might show this a little bit more clearly.
That's true, actually, yeah.
So I think that would clarify this, because over the length of a given string, here's how well it's doing in terms of, I think it just captures this a little bit better.
Yeah.
So basically what you want to have is like number of misassemblies per 100 KB assembly or something like that. That would also
yes.
address it. Okay.
Well, that's something we tried also, but it's, well, I don't have to show this because the scaling is a little bit off. Yeah, we try to normalize this somehow. Yeah. Okay.
The same comment.
Okay. Yeah. No, if you have ideas of how to present the data, maybe, and how to, what to look at, let's make a list of all these things, and then we try to generate all these different things. Okay. That's it.
Okay,
Thank you very much.
Alex.